Many thanks for the introduction. Before I begin, I would just a little bit to the correction, mainly since I was not fully clear who would be the audience. So I finally decided also in discussion before to give some short introduction in general about the topic of artificial intelligence and machine learning, and then also prepared a few topics considering my work from the recent years. However, in this case, main point would be giving a very brief introduction, just letting the people know what I'm talking about, what I'm working on, and this would hopefully open some collaborations in future. In this way, I will start, so hopefully it's working, with a short overview of my presentation. In the beginning, I would like to really focus on the topic, what is artificial intelligence? Because also when I was having the talks before, was also adapting my slides in this direction, just to make clear what is my personal understanding, what is the general understanding of artificial intelligence or machine learning. Then I would like to give a short introduction to some topics like linear classification and neural networks, which are currently in big hype. Then which I call here applications, are mainly my own work, which would maybe, depending on the time which is remaining, I would select one of them to talk about, depending also on your interests. And finally, I will not talk about this, but in this case, I would assume that also the slides would be made available in some way, that there is some kind of literature overview which covers freely available literature and also general literature on the topics I'm talking about. So then starting with the general topic, artificial intelligence, and this way I call this machine learning versus artificial intelligence. Because the main point is that many people are mixing up these topics and don't know how to classify this. And from this point of view, I would like to give you a general overview of how these terms, machine learning and artificial intelligence, are understood, and also giving my personal understanding of these terms. In general, if we're talking about artificial intelligence, going back a few years, the general definition was that computers should demonstrate human-level cognition. In this case, we stood at that time playing chess, driving cars, flying planes, and in particular, passing the Turing test. So in this case, making everything a little bit more interesting, I would also invite you to do some kind of collaboration with me. Is any one of you already heard about the Turing test?
Not really.
No one. Okay. Turing test was named after Alan Turing, the famous computer scientist. And he was describing a test. If you're interacting with a machine, if you're talking to a machine, then you should not be able to differentiate if you're talking to a person, to a real human, or to a machine. If you're used to some kind of these bots, which are nowadays often used by a service hotlines, you see this is not working very well. But in particular, the main idea was you should be able to talk to a machine, not recognizing that you're talking to a machine. So this is what long time ago was assumed to be artificial intelligence, really meaning a machine would behave like a human. In contrast, machine learning is something different by definition, meaning that computers can learn from experience. Also, a human is typically learning from experience. However, in this case, the main idea would be that we can adapt to new tasks, to new environments. And typical examples, which are often named here, are face recognition, speech recognition, or which was often recognized is the recognition of filter spam, considering the emails. So in this case, the main difference from this, let's say, historic description would have been that computers learning from experience, which means that they're doing some kind of statistics. So this is what the difference between artificial intelligence and machine learning was described for quite some time. And in this way, I would like to show you some kind of diagram, which is typically also shown in textbooks, which is described that way that the overall field is called artificial intelligence. Then a subpart of artificial intelligence is considered to be machine learning. Then within machine learning, there's a topic called representation learning, which is typically what we are dealing with when we're talking about machine learning. And just a small subfield of representation learning is then deep learning. And this is now the point where I would like to talk about, just to make it clear the difference between artificial intelligence, machine learning, and deep learning. Before going in more details here, I would just explain what we assume to be learning. And therefore, I would like to cite a few famous people who have been spent a lot of time for thinking about learning in general. The first quote I would like to put here is, learning is constructing and modifying representations of what is being experienced. Once again, in this case, you see that experience is very important. This is something we can consider from human learning, but also these ideas are going somehow in the direction of machine learning. The next quote I would like to put here is, learning is making useful changes in our minds. It's more or less going in the same direction, however formulated in a slightly different way. The next quote is, learning is improving automatically with experience. Once again, experience is coming in this case. And the last quote, it's rather long, so in this case, I would let you to read this on your own. But in this case, what I wanted to show here is that also from these years which are given along with the quotes, that over the years, over the decades, learning was defined in a different way. However, it mainly going back to the term of experience, meaning that we're changing something, that we're changing the mind, that we're improving our experience, that we're improving our knowledge. And this is in common of all of these definitions, and this is also how learning is understood in science. Then, what next point I would like to go with you is now a transition from learning. What I've told you up to now was mainly the human learning, and now the main point would be to have the transition from human learning to machine learning. And here, the main quote I would put here, there's no official book or other citation for this, but this is something I've taken from the website of Thomas Dieterich, who is one of the godfathers of machine learning, if I'm allowed to call him that way, is the goal of machine learning is to build a computer system that can adapt and learn from the experience. What you can see here is exactly the same we had before for the human learning, is that we would like to learn from experience. However, in this case, the main point is that we're now talking about computer system. And this is exactly the difference between human learning and machine learning, that now we have a computer which is in the center of our thinking. Now, coming from this very general description, I would go a step further to a little bit more technical description. Which means, in our case, when we're talking about computer systems and experience, the main point what we're dealing here with is we finally breaking everything down to statistics. In this case, we have variables, we have a system, and the main point is we would be interested in the relationship between these variables. And then there was having exactly the same discussions before with the people who had the first slots of the day, is to getting these kind of relationships we're interested in, we're coming up to some kind of optimization problem where we learn a model based on the data from past experience. So from this way, the main difference between human learning and machine learning in this case is that now we're building on statistics, that we're building up a model and trying to cover this model in practice. So we'll skip this one here and then continue with further categorization. I was telling before was the main point I would like to focus here is to say that we have different definitions and understanding of artificial intelligence machine learning. And now what I was telling you before was the traditional assumption of the difference between machine learning and artificial intelligence. And now is something which will come, because we've seen that there are many, many companies, in particular in the US, which are really fostering the field and really the big players. And now the European Union would like to get a key player in this game. And therefore, the European Commission defined some kind of goals, some kind of topics which are considered to be artificial intelligence. Machine learning is clear from what you've seen up to now is definitely a part of artificial intelligence. If you're talking about autonomous systems, flying a plane, driving a car, so this is also typically part of artificial intelligence. Interactive systems, if you're talking to a machine, was talking about the Turing test, also this makes sense. However, then there are coming a few other points, which at least from my personal point of view, do not make as much sense as those points I mentioned before. These are hardwired automata. This was artificial intelligence dating back to the 1970s and the 1980s, just applying statistics and everything which is related to processing data. As long as I would say that these points here are clear facts, clear applications of artificial intelligence at some point, at least from a personal point of view, I'm not sure if we should count this in. But it was exactly what I was discussing before, that now it's a hype on artificial intelligence, meaning that everyone wants to do artificial intelligence, everyone wants to sell artificial intelligence. So many applications are sold as artificial intelligence. However, in this case, it's questionable if this really could be counted in. So from this point of view, we'll come to the last point of categorization, now giving you the common understanding, which is typically in community, also in computer science, is that if you're talking about artificial intelligence, we typically mean deep learning. So these terms are typically used interchangeable. Then there's, I personally call this abuse understanding. Let's say every time data and some kind of statistics is involved, we can talk about artificial intelligence. I would say this is some kind of abusing artificial intelligence just to make money, just to make business. And then there's my personal understanding, meaning that machine learning could be based on some kind of predictive statistics. And in this case, which is often the case, that artificial intelligence is then used as a synonym for machine learning. So this is just to make it clear, there's some kind of philosophically discussions on how to define this, but this is now what I wanted to give you here, just an overview of different opinions, of different kind of understandings. And then it's on you to find out what is the best definition for you. So this was now the first part, just giving a very crude, a very brief introduction on the terms of artificial intelligence and machine learning. And now I would like to continue in more technical details. So since I didn't know in the beginning who would be in the audience and what would be the prior knowledge, now this could be considered some kind of very basic lecture of getting into these topics. And also these topics have been a little bit changed before, of also the discussions I had before this talk. And therefore I decided to talk about two topics. The first one is here just linear classification, which is the easiest way of classification. And the other point, which is the most interesting for most people now, is neural networks. And also here, the comment from my side, neural networks are a very powerful tool, a very useful tool. However, you have to really think about if it's meaningful to use it. From this point of view, I decided finally to talk about these two topics in more detail. Before we go in the technical details, I just would like once again to give you some kind of overview of main topics you're dealing in machine learning. First thing, we was also talking about this before, is everything which is related to data minimization and feature selection. In this case, this means that we typically are dealing with huge amount of data, and the main point is, on the one hand side, that we would like to reduce the amount of data to deal with for computational resources, for memory reasons. However, the other point, which is as important, is that there's much data available which does not contain any valuable information. So here, if we're talking about data minimization or feature selection, this means that we're reducing the amount of data to valuable information. This is still something which is very, very important, because often we cannot apply models if the amount of data is too large. The other point, this is finally what I would like to focus on, is classification, meaning that I've given an unknown sample and I would like to assign an unknown sample and specific label, which I do not know before. The next point is regression. In this case, the difference to classification means that this is not really a label, but in this case, we can assign any value to a sample. And in this way, the problems are very similar. However, we have to differentiate between classification and regression, both involving a specific sample. And the last point, this was also something which came into my mind before in a lot of discussions, is the theme of clustering, just to find out which samples belong in the same cluster, which samples are somehow similar. So these are typical problems you have to deal with in machine learning. And in this case, just for reason of simplicity and taking into account the time resources, we'll just focus on classification in the next few minutes. If we're talking about classification, before a little bit more technical, means that you would like, and this is very important, every time we would be thinking things like that, you're trying to estimate a function. A function from an input space X to an output space Y, with the goal, as I said before, that we have an unknown sample X, and then we would like to find the function f, assigning the value X and output value Y. And here, what is important if you talk about classification and learning classification, means that during the training, this means that we are given a pair consisting of the data point X and the label Y. So the goal would be giving a set of pairs, data and label to find a model F. And here there are several different approaches which can be used for that. I just name a few of them because also from previous discussions, a few of those points came up. This is nearest neighbor classification, linear classification, support vector machines, random forests, boost neural networks. So there are many, many different kind of classification approaches which can be applied in practice. In the following, I would talk about two of them, which is support vector machine and neural networks. So to start with support vector machines, I would like to talk in general about linear classification. So in this case, once again, I would like to invite you to work together with me. Here we have a problem consisting of a set of two clusters. We have the red squares and the blue dots. Now the question for you would be, how would you separate these two set of points?
Do you refer on how to separate them in the space?
Yeah.
You could make a diagonal line to separate them, and then you would have different space, one for the red and one for the blue.
Exactly. That is exactly what we're doing here. And then this is the point where now linear algebra comes into the game. You can see here what we would like to do at this point. We would like to have here, the simple case, a line. In the more general case, we're talking about a hyperplane. This is this one here, which is now separating. Okay, in this case, it's not that linear. We are trying to separate the blue dots from the red squares. And what is important here, just from a technical point of view, is that we're now using here the orthogonal projection of this separating line. And then the goal would be to find the projection of the data points. I will show you this later on. Do this vector and then defining, computing the sign of these values. So this is a very, very simple explanation of what we are doing with linear classification. However, here the main point, which is now important, is how to find this W. How to define this separating hyperplane. What we would like to show here is now that we have some problems, because if the data is separable, then they're giving many feasible solutions. Or more general, if the data is separable, then we have an infinite number of solutions which is possible to be applied here. So this is nothing we can really deal on in practice. So now there are different ways of how to define a specific hyperplane, a specific separating hyperplane for this problem. And one of the most successful approaches are now the support vector machines. And now the idea would be, I was telling you before, what we're doing here, we try to introduce some kind of model. We would like to have some kind of organization problem. And now the goal would be to find a specific hyperplane which has some kinds of constraints which are feasible for future classification. And this means in our case, what we're doing, we would like to find the solution that way, that future unknown samples are classified most robustly. And this means in our case that we're not just searching, in this case I will change the color, that we're not just searching for the separating hyperplane, but that we're also imposing some kind of constraints. And what we would like to have in this case is now that we have a margin around this separating hyperplane, which means there's a hyperplane and there's some region around the hyperplane where we do not have any further samples. And in this way, we can guarantee that future samples which are not represented here within this data set would be also separated very well in the future. So in this case, we would like to maximize the margin, and therefore approaches like that also called maximal margin approaches. And if you're wondering where now the name comes from, just a short explanation that if you have those points here, which are exactly on the margin, these are the so-called support vectors. And if you would go into more technical numerical details, you would see that these support vectors have a big influence of the whole computation and the optimization of this problem. But just to make it clear, once again, the simplest way of classifying a problem with two sets would be to find a linear solution. And one successful way is the support vector machine, where the key idea is to define the hyperplane that way that future samples would be classified most robustly by introducing the margin, as you can see here. Then coming back to what I told you before, the question is, we are now interested here in this case, in this hyperplane. And in the next minute, I would like to explain to you why now having this projection is of importance. Because finally, in this case, I'm showing an example with 2 dimensions. However, this could be any dimension. But the final point is, the final goal is to project the data to 1 dimension where we simply can do some kind of thresholding later on. And this is exactly what you can see here. We have now this classification function. Here's the hyperplane. This is then the orthogonal projection. And you can see that all of these red squares are now mapped to this line here. All of the blue points are mapped to these lines here. And what you should see at this point is that we now really have here the line, and that this would be now some kind of threshold where we can separate the data. Or, in this case, just projected to 1D. These are now cleaning this, maybe you can see this once again, that exactly these points, which are shown here, these points, and these points, which are shown here, are then these points. So whatever dimension we have in the very beginning, in this case, we can project the data to 1 dimension, and then, see before, we have the signum, just getting the signum. In this case, we can do a very easy classification. And the same idea also applies for different kind of approaches. The classification is always the same. However, you're optimizing different optimization problems. And this is something which is very important for you in practice. If you're talking about machine learning, something I have to tell you, there is no golden rule, no golden method you need to use. For specific problems, there are specific approaches which would be most viable in practice. And therefore, my typical advice at the beginning is, before you try anything else, just use the linear support vector machine, just see what you get out. And if you're happy with the result, then there's no reason for using more complex approaches. Okay, then in this case, since maybe some of you are familiar with R, typically in teaching I like to use R because we can boil down very complex approaches to just 1 line. And what you can see here is that even for those people not really familiar with programming, it's just a 1-liner for estimating the model. It's just a 1-liner for predicting the model, which means that also people who have never done any programming before would be able to use this very briefly, if maybe very short time of introduction. So this was the first thing I wanted to tell you, just to show you that using simple approaches, getting the idea of how to do a linear classification. The next thing I would like to tell you is about neural networks. As I said before, currently deep learning and neural networks are to be considered to be artificial intelligence. And from this point of view, would also give you a very, very brief introduction to neural networks. Typically, you would have the chance for giving a lecture for a whole semester. Now you would be happy to get the whole thing within 10 minutes. Main question is, what are neural networks? What was the motivation for dealing with neural networks? Once again, I would like to invite you to work with me. You've seen before the simplest way of separating data would be defining a line, would be using a linear hyperplane. In this case, how you would separate the data which is shown at this slide.
You could make 2 circles for the red, or like a kind of like a irregular pattern.
Something like that?
Yes.
Yeah. In this case, you can see that's definitely not a linear one. So something just was once again to increase the pieces here. What we would like to have is once again two regions. Here, one region which is covering the red squares, and the other one which is covering the blue dots once again. And you can see if the data is more complex, if your problem is getting more complicated, then linear approaches are not doing a good job anymore. And here now, this is the main reason, this was something I told a few people before, is that the main reason or the main motivation for using neural networks is that we can approximate, and this is very important, that we're not getting... Okay, and the main point is that we're not going to a closed form solution, but the approximate solution, and which is important for any nonlinear function. And I said before, as long as you're able to define your problem as a function, as an input-output mapping, then you could use a neural network for doing so. Now the question would be, how do we get this? And in this way, just having a very brief overview, in this case we have a graph-based approach. You see now next what the graph is, and that in this case it's biologically inspired. We're a little bit careful with these terms, because if you're now talking about biologically inspired and be mimicking the brain, in fact, what we have there is now the state of the art from the 1960s. So in this case, we are not really mimicking the human brain, but there's still many ideas which are still valid. And the main point that we have here the universal approximation theory, which is saying exactly what was telling here, that any nonlinear function can be approximated using neural network. This was shown twice for different kind of problems. And I would like to show you the basic ideas which are behind a neural network. And here we have to consider 2 points. The first thing is the singing neuron, and the second one is the multi-layer architecture, where you now see what a graph is. Considering the biological neuron, maybe you would know more about biological neuron than I do. So from this point of view, I will not talk about this one, but going directly to the mathematical neuron. However, the main idea is the same. What we have here, we have some information, we have some signals which are arriving here at the neuron. These signals are summed up. And then the main point is that we have here now a function once again, which is a nonlinear function, where all of these signals are summed up and then transferred typically to a value between 0 and 1. So from this point is exactly what was happening in the biological neuron. The signals are coming in, they are accumulated in nucleus, and then the signal is forwarded. And the same thing is also done in mathematical neuron, where we have input signals with an output signal. The main point is, and once again, what comes in here is now linear algebra, that they have a weighted sum of the input signals, which are then used in the output. And this is very important, because just to understand what we're doing later on is that the whole learning we're dealing with is finally dealing with these W's. So we have the input signals, we have weights for the input signals, and the main idea is now to learn these weights. The specific input is matched to a specific output. That's the first thing, the singing neuron. The second one we have to deal with is then the multi-layer architecture, which means that, and this is the important point, why neural networks are that successful, that in this case, we have different layers, which can be seen here. And the same thing as also was here in the visual cortex, that the different layers are representing different kind of information. What you can see here, that starting from very simple contrast information to simple structures like edges, to more complex structures like corners, to higher level structures. So the main idea is that if a signal is traversed through the visual cortex, we're getting more and more complex structures which are in this space then represented. And from this point of view, these are the two main concepts which are of interest and which are also politically inspired, meaning that the information accumulation within a single neuron is mimicking a little bit what is done in the human brain. And the second point is also that we have the same thing here in this multilayer architecture from the visual cortex, meaning that from layer to layer, in this case, the information is transferred to a higher level and is represented then also in a higher level. And then the main point, and this is interesting and this is important, is now that in this way we can deal with different problems. As long as our problem can be formulated as a function, we can deal with different problems. These are multi-class classification, regression, and clustering. And since all of these terms have been represented in the discussions I had before, they obviously all of them are really meaningful and important for you. And from this point of view, it's really necessary that you can see that all of these problems can be solved using neural network. However, it's very computationally very demanding, so you have to think about if this is meaningful in this case. And the last point I wanted to show here for neural networks is now giving just an overall idea of how neural network training can be performed. And then I would like to show you this on a simple practical example. No idea at all. Okay, now the main point is that I would like to give you a crude idea of how neural network training is working. And this is also the reason why the whole thing is taking that long, because you will see that in this case we need an iteration process which needs to be run several hundred times, and this is not very efficient in practice. What I was telling you before is what we're doing here is just using some kind of weighted sums. So what is done in learning is that we are optimizing, that we are changing these weights. So this is one of the big drawbacks of neural networks, is that we have to initialize these weights in the beginning, typically in a random fashion. This is not the best case, however, still the best we have up to now. And then we have some kind of iteration, which means that we're providing new samples. These are propagated through the system. Then we get an output. Then the main idea is just to check how well does our system really describes the desired output. Then, with the so-called back propagation algorithm, we are adapting the weights, and then the whole thing is repeated until we converge. So just in one sentence, the main idea of neural network training is nothing else than just estimating the weights such that the finally estimated function is representing the input very well. And this I would like to show you in a very simple illustrative example. What you can see here is a very simple neural network. You can see here we have 3 inputs. Could be any kind of number. We have one hidden layer here. We have an output layer just consisting of one not at this point. Anyway, this could be as complex as you would like to do. Another important point is what you can see here. We have now different input samples. We have the according label, and the goal would now be for these 3 samples to assign the value 0, and for these samples to assign the value 0. And for this one here, we would like to get 1. And now what we're doing is, after the random initialization, we're showing a sample to the system. In this case, it's the first sample here. We have the input 1.4, 2.7, 1.9, and this should provide the output 0. In our case, we get the output 0.8. Here in parallel, I'm showing you the decision boundary obtaining from the system up to now. You can see here that this randomization does not do a very good job. If you continue this interpretation, you see we get a result of 0.8. The desired output was 0.0, which means that we get an error of 0.8. And now comes the backpropagation into account, meaning that we are now adapting the weights of our system such that this error can be reduced. So we still have the same decision boundary here. Then what we're doing next is once again to present the sample. Now you can see here the changed decision boundary for this new sample. See here we get the output 0.9. Desired output would be 1. Once again, the same game as before is that we now compute the error, which means desired output was 0.9. The predicted output was 0.9. The output we got, the desired output was 1.0. So we have an error of minus 0.1. In this case, once again, we adjust the weights based on this error, and once again, getting and changed in different decision boundary. And here now the main point, which is of relevance, is now that we're repeating this thousands and thousands and thousands of times. And finally, if we converge, we would finally get a decision boundary, which is solving this problem very well. And this is now also the point by the training of neural networks that they are that time consuming, because we have to repeat this again and again and again. You have to show the same time to the map model again and again. And this is what this model makes that complicated and that computational demanding. So once again, you would get a good result. However, the problem would be that in this case, you would need quite some time for getting this result. Then the next thing I would like to show you is now a practical example, just to show you that this is really working in practice. And in this case,
sorry, may I ask a stupid question? You say you have to repeat it 1,000 times. This means you need to have 1,000 input data, or do you repeat it with the same input times?
Okay, so sorry. Okay, now that is a good question. In this case, this means you're having the same input data, and the same input data is then applied to the system again and again. In this is called epochs. You will see this later on the example I'm showing you. The main point is you have the same data, but you have to provide the data to the system again and again. That's the main point.
And does it remember which one was used and what was the error, or does it not know? You know what I mean?
No, in this case, this is now the drawback of system like that. That in this case, you have, from a statistical point of view, you know, if you're doing this again and again, you would finally end up in some kind of convergency. However, you're not storing this kind of information.
Okay. Yeah.
So there might be a little, let's say, that's a little bit more sophisticated approaches for doing so, but the most common approach would be just to provide the data again and again. And for sure, there are many, many points which should be considered to make this more efficient. But in the most common way, you're just providing the data again and again and not dealing with this kind of information.
Thanks.
Okay, then once again, I hope this is not crashing here. This is the playground of TensorFlow. What you can see here is a very, very simple neural network. We have here two inputs. We have here a hidden layer with 4 neurons, and here's the output. And the goal would be, what you can see here, to separate the blue dots from the orange dots. And now just have an eye on here. There are the epochs. And one epoch is one time the samples are presented to the system. And now I'm starting the whole thing. And what you can see here, that now the data was provided, I can stop here, 100 and 200 times to the system. We can now see that here now the blue points and the orange points can be separated. I'll show you this once again.
So how do you decide on the number of neurons?
That's exactly the important point, that you don't know this in before. It's typically based on the problem. And what I would like to show you is the reason why I typically like to show this kind of setup, because here we can now increase the number of neurons. Then I would see that now if we increase the number of neurons at this point from 4 to 8, we now after 40 epochs, we got the result. If we now reducing the whole thing, run this again, then you can see if you're just using 2 neurons in the hidden layer, we are not able to solve this problem. This is exactly what the humans have to do in this case, because even if you're running the whole thing forever, we would not be able to solve this problem using this architecture we've chosen here. But once again, if we now increase the number of neurons here from 2 to 8 once again, you can see that after 30 epochs, we are done. And this is something which is very important also in practice, that you need to be aware about these details. Just seeing in this case, increasing the number of neurons would give better results and would allow to get some problems solved.
Why not use standard, what is the cost of having more neurons? Put it this way. So why don't use 1,000 neurons then?
You can use 1,000 neurons, but in this case, the main point is that in practice, the more neurons you have, the more parameters you have to calculate. And at some point, you're running out of data, which means this is also the reason why typically a deep learning is requiring a huge amount of data, because you would have to learn these parameters. In our case, in this case, you can see here, you have now 2 parameters here and 2 parameters here, so we have to learn 4 parameters. If we would use 1,000 neurons at this stage, then the point is that we not have to learn the 4, but we have 1,002 parameters, and probably we would not have enough data for doing so. This is the reason why we have to find a meaningful trade-off between the number of samples you're using and the complexity of the network. So just using more and more neurons would work, but it's not always meaningful, because you would have to estimate much more parameters.
Okay, so this explains the cost. Thanks. But
yeah.
And then I have another question. How do you determine on the number of hidden layers?
This is exactly the same point. What I would like to show you here is exactly that now, instead of using more layers here, I would like to increase the number of hidden layers to see that now I have the same number of neurons. So we had here now 8 neurons, so 4 hidden layers with 4 neurons. Then if you start the whole thing again, then we can see nothing. So in this case, what you can see that we have exactly the same number of neurons, but in this case, you see that really also the architecture, which means how the layers are arranged, how many neurons are per layer of your importance. And this is something, once again, what we can see here. If we increase the number of hidden layers, then also the training is getting much, much more complex. You can see here now, we needed 400 epochs until something was changing here. And this is exactly the point which is important to just from experience to see which kind of architecture is meaningful for a practical application. Here you see there's still some things changing, so we're not converged. However, we'll see if we would make it. But in this case, you can see here we have the loss, which means that the query optimizing. You can see here there's nothing changing. So at this point, we assume that we would be not able to get a convergence here. However, if we change this once again to 3, 2 hidden layers with 4 neurons per layer, you can see that once again after 60 epochs, you're getting a result. And here you can see here that just having the number of neurons is not important, but exactly what we can see here that also the architecture is of importance. And if you're going then for deep learning in terms of convolutional networks, this is some way of representing particular image very well, then there's a huge decision and the huge effort which is done on the architecture. And this is what this example shows very nicely, is that we really have to think about the architecture, what is meaningful, how much effort you should spend in the design of this kind of network. In this way, you would find the link then also in my slides if they are provided later on. And this is really something for beginners. Before you start to implement anything on your own, you would say the very first thing would be to play around with something like that, because here we can get some impression considering convergence, speed, complexity of the network which is required. And from this point of view, I would say this is really something which is very useful, in particular for the very beginning, and you can see, is it meaningful for you, for your task, to deal with this kind of problem?
Sorry, just one question. How about overfitting if the data are not so nicely separated, like in the example you're showing us?
Yeah. Also in this case, you also see just for playing around, even typically don't like this kind of data. Also here you will see that it's able to separate this data. The main point is, and this is really a big problem for neural networks, because if we can run it here, we will see that also we will be able to get a meaningful result. Maybe we have to get a more complex architecture for this one here. But the main point is that this is exactly what you can see here on the left side. We have here the training loss and the test loss. So the training loss is not a loss function, it's optimized for the training data, which means that in this case we're also quite good in modeling the training data. But what you can see here that the test loss for the data which was not used for training is not fit very well. And this is in particular a big problem in neural networks, because, as I said before, if you're making the network large enough, if including many nodes, then we would be able to represent the training data very well. However, there's no guarantee at all that we are getting a model which is generalizing very well. In this case, overfitting is a big problem, and therefore there are several ways of doing some kind of realization to avoid this. But typically, if you're not doing any kind of realization and just using a big network in huge architecture, then you would terribly run in overfitting problems.
I have a simpler question. The last 2 neurons tell me that I have 2 classes. So if I want to have 3 classes, then I would put 3 neurons there, or is this wrong?
Yeah. This makes the whole thing very simple. So in the simplest case, then you have just 3 neurons, meaning that finally that the class response would be the neuron where you're finally ending in. There are other ways. If you represent the whole thing via regression, then you have some kind of sigmoid function in the end, softmax function, where you finally be able to also provide a regression value. But the simplest way in this case would be that you're using, in this case, 3 nodes in the end. And from this point of view, this makes the whole thing very flexible, because you can decide of how many output classes you would like to define here. You can also define the number of input samples. So from this point of view, very flexible. So if you don't know anything about the structure of your problem, then this is a very easy way to define a function which can be used to solve the problem. But once again, I would just ask you, play around with this tool. This gives a lot of impression for this task. Further questions to these results? Okay, if this is not the case, then once again I would like to show you, this is in this case my last slide I would like to show to you, is now that besides what you've seen here in the online tool, you can also see that here using, in this case once again R, because it's very simple to install, you don't have to care about any things like GPU, etc. Then you can see that there are some parameters you have to set, and from this point of view, it's important to understand the basics, just to know what the learning rate is, what momentum means, what batches, etc., etc. So there are a few parameters you need to understand, and once you understand this, then this would be everything you would need for training your own neural network for your own problem. And this is really something also recognized from people without any technical experience. Just using this primer allows you for setting up your own neural network in just a few minutes.
You're still showing us the web page from before. Do you want to show us another slide, or?
Okay, sorry. Can you see now my code?
Yes.
Okay, sorry for that. I was sharing the screen, so a little bit confused. Okay, now once again, just to repeat, what you can see here now is just the simple code for training neural network. Once again, you can see in the simplest case, you would nothing else than just a one-liner. And then you have a few parameters to set, which can be used to learn the neural network. And once again, also as we've seen before for the support vector machine, it's just a one-liner also for doing the prediction at this point. And as I said before, if you're just having a running code like that, then it will be an easy thing for you to run your neural network on your own. In particular, if you would be interested, they could also provide a few of those code samples which are running out of the box. So if this would of interest, I can provide this later on. Okay, as I said before, just to browse over, you can have a read on this own. Summarized a few books which are covering these topics, which is from one hand side for experts, but also for starters. And many of them are really available on a officially free version. And in particular, there are also some books which really show that also in machine learning, some kinds of population kinetics are really coming into account. This was a big hype, as you can see here, 20 years ago. But there's still many ideas why this is getting more and more important. In particular, from those of you who are familiar with technical issues, if you're talking about optimization, one of the key points would be to get a global optimal solution for optimization problem. And once we need things like that, then all of these ideas of genetic algorithms, genetic programming are really valuable choices which can be applied here. And since I was talking before, there are many parameters to search for. There was a question about how should the architecture would be. And here, approaches like that are really used then for kind of architecture search, really meaning, okay, how should the architecture look like to get, in this case, best results. From this point of view, many thanks for your attention. As I said before, since I was not sure about the kind of audience, I was trying to give you a very brief introduction and a general idea of machine learning, also giving the relation to artificial intelligence, since there already have been some discussion and questions, but yeah, you're invited to continue this right now. Thank you very much.